Swayam Prabha. Digital India. Educated India.
So students, today I will teach you one more very important topic for PCB's biosensor development. As you know, I taught you already that PCB can be a useful addition for the biosensor development, right? Because why PCB is very important? You know that without PCB you can't see any electronic instrument, and we in our India, even in your local place, you can see that easily you can get the PCB, and we have very good PCB fabrication technology. Let's use them for biosensor development. And important things that we can easily coat a gold layer on the PCB substrate, and that substrate, that is gold coated plate, we can use for biosensor development. So that topic very deeply I will teach you today, like how the PCB can be used for biosensor development and how we can clean the surface for PCB, that I already started, I will continue today, and then their impact of surface for biosensor development. This is very important things that today I am going to cover. So mainly that's why I will cover today first the PCB based biosensors, and the let's take one example like glucose quantifications. Okay, so glucose quantification, that I will teach you on PCB. As I told, the lab on a chip technology, you can remember what is the lab on a chip technology? Means all the laboratory experiments that you are doing, like sample purifications, sample then amplifications, then detections, everything can be done on a single platform, right? That is the lab on a chip technology. And here why I said lab on a PCB, because that chip will develop on printed circuit board. So PCB means printed circuit board. So that PCB I will teach you very basic things today. So let's find out the basic keywords. If you want to study more in details, please search that PCB that's related for the biosensor development. And for example, today I will cover one example, that is the glucose sensor. Okay, I think few things I already covered last class. That printed circuit board is really important because of mainly the integration technology, that we can easily integrate many things, right? You can remember last class I showed you, just I am summarizing that we can easily integrate this. You can see microfluidics, right? You can see this channel serpentile, this is the microfluidics channel. So there may be a sample, right, sample inlet. So what is this? Where you can easily drop the sample, and then this sample will flow through this microfluidics, right, and then it will come to your detection area. So this is the your detection area. So one is your working electrode, one is your counter electrode, one is your reference electrode, and this is your adapter where you can connect with your potentiostat, right? So through this potentiostat, maybe you can apply some potential. Which potential you want to apply? So you have to select a electrochemical technique. So if you want to apply the potential, maybe you can select chronoamperometry, CA, right? Chronoamperometry, you can remember, right? Or you can apply chronocoulometry, right? Coulometry, that is CC. Even you can apply cyclic voltammetry, CV, cyclic voltammetry. Just you can play around the software here, and based on this 3 electrode system, right. So, we need 3 electrode system, why I already taught you last class. This is the 3 electrode system, right. That 3 electrode system we easily integrate on PCB platform. See, there is a different shape you can see, like different PCB we can design, and you can see the different layer. It means on the top of the PCB biosensor that we fabricated already, here also we can integrate a different layer based on the microfluidics, based on your requirement. Even you can see this this serpentine, that is the microfluidics, here sample will flow, right. Sometime you may need to increase your temperature of the solutions, sometimes maybe 37 degrees Celsius, your reactions is the best. So, what you can do on the back of this microfluidics, you can use some heater, localized temp, you can heat the in this area, local area, and you can increase the temperature of the solution. That is the concept of PCR, that polymerized chain reactions. And sometimes you may need to increase the temperature, sometimes you may decrease the temperature. I mean, you can heat, cool. Cooling and heating also can be done in the, these solutions you can use, you can play like which temperature is required for your reactions, right. That things also you can try with the printed circuit board. Let us show you this all the technology like PCB. This is the another design of the PCB that I showed you last class. That PCB I already used like 3 electrodes. See, here like this is a multiplex PCB, right, multiplex PCB. Why I am saying this is the multiplex? Because you can see 1, 2, 3, 4 see unit there. So, here maybe you can try 1 detection, here 1, here 1, here 1. So, 4 detection can be done simultaneously. That is a multiplex printed circuit board. And last class I already taught you. Let us summarize that this PCB, when we received from factory, there is lots of contamination. We need to go for some pre-treatment. We need to go for some cleaning method. You can see like before cleaning, you can see almost there is no peak. This is just like if you see 1 millimolar K3 FeCN6. So, here iron is the 3 oxidation stage. See here, if you see like first reduction, because we started from 3 Fe3, then first reduction and then oxidation. See, at the beginning before the cleaning there is no peak, but after the cleaning we are getting very good peak. So, cleaning necessary, and I showed you right already the AFM images. See, this is the before cleaning, there are lots of organic stuffs there, and after the cleaning the surface is very clean and you will get very good cyclic voltammetry. Now, today why I showed you again this figure, because I wanted to start one again important topic today. Means after the cleaning the surface, you have to be very much careful that your surface is properly clean or not. Although you are following like your best cleaning method I taught last few classes, you can remember first the organic cleaning. Organic cleaning, what is the organic cleaning? Like one first acetone, then ethanol, this, and then third after the organic cleaning with these two, acetone and ethanol, for 50 minutes sonication, bath sonication, then you can go in the DI water. DI water you can take, and you can go for again 15 minutes sonications, right. So, these sonications will help to remove some organic contaminant, but still some contaminant may be there. So, you have to remove very clearly. So, you have to use like hydrogen peroxide, ammonium hydroxide and water mixture. This is 1:1:5, and let us sonicate it again for 30 minutes, or you can boil, not boil, this is just heat at 80 degrees Celsius for 1 hour. So, you may get very good surface, but sometime after the cleaning you may not achieve your required cyclic voltammetry what you are expecting. That cyclic voltammetry you may not achieve. So you may ask why you said that ammonium hydroxide, hydrogen peroxide water mixture 1:1:5 ratio is getting very good. But in the PCB case, when we are getting the printed circuit board from the industry, then we are going for the this very vigorous cleaning, but still you may get some bad data. It depends batch to batch variation during their fabrications. Some organic stuff that may cover the active side of PCB surface is very strongly. It may not remove. Also, it can also, if you try like very vigorous cleaning, also it can damage also the surface. So you can guide your PCB factory. I mean, they have their own R&D sections. You can guide them that we need this kind of surface, we need this kind of surface cleanliness, this kind of surface roughness, and that is good for my biosensor, and they can fabricate for you. Okay, this information I will share with you now, that you can tell and they can fabricate for you. They can take care their fabrication accordingly, and they can give you those surface. See here, I will show you 3 figures of cyclic voltammograms that we received 1, 2, 3, right? These 3 cyclic voltammograms we received after cleaning. But problem is that what cleaning? Means just same cleaning that I told you, like organic cleaning, ammonium hydroxide, hydrogen peroxide and water, was all the cleaning we followed. But some cases you may get very good cyclic voltammetry in the K3, Fe, CN6, this mixture. You may get very good cyclic voltammetry. It means this surface is really good and you can use for biosensor development. Without proper cleaning, don't use them for biosensor development, because you may not get the best signal. There may be a reproducibility issue. See, in the second and third case, you can measure the delta E value, delta E. So this is the, I am just repeating again, please try to remember now. So in this cyclic voltammogram, just try to remember. So this is the oxidation peak potential, right? So this is, I can say E1, and this is the reduction peak potential, right? So this potential, the reductions happen. So I say this is the E2. So I can say delta E equals to E1 minus E2, right? So E1 and E2, if you calculate this value, this delta E value, we can use a very important parameter. How? Because this will give you the surface behavior, if your surface is properly clean or not. See, in the first case, this surface, it looks like very clean. That's why E1 and E2, they are very close, right? I also taught you, you can just try to remember, if these are very close, it means your reactions on the surface is very, means reversible or semi-reversible, right? Reversible. But if delta E, delta 1 is not very close, see, in this case, oxidation reduction speed, they are not very close. So in this case, so if I say this is the delta E1, and in this case, this one delta E2, and in this case delta E3, see, delta E value actually increasing, right? From this value, you can predict the surface. It means this is the best surface, and then slowly your sensor surface is actually not much good, because this surface showing slowly irreversible phenomena. This oxidation reduction is not happening in the very not reversible way. So this surface is not so good for the biosensor development. This surface is not so good after the cleaning. Still some organic stuff, some contaminant there. That is the conclusion from this cyclic voltammetry. So 1, 2 and 3, this cyclic voltage we compare. So, here actually we compare first and second scan, means we can try the many scan. If there is a variability, there is a change of the current or potential during the scan. So, in the first case is so stable the surface. If your surface is not stable during the different scan, you may get different value. See, their current changes, their potential can be changed because your surface is not that much stable. That is another information you may get from this cyclic voltammetry. Okay, clear? So, this delta E1, delta E2, delta E3, this value you have to calculate and then you have to take the decision. This is the summary of this slide. Let us come the very important images of these 3 cyclic voltammogram that I have showed you in the last these 3 figures. Let us take this AFM image, atomic force microgram image I wanted to take, and then I wanted to see that surface how it looks like, right. See, if this surface is very clean and you are getting very good cyclic voltammogram, in this case you see the surface looks like this, and root mean square means RMS value. So, this is RMS, root mean square value, in this case 18 nanometer. Second case, see, this is the 41 nanometer RMS, 41 nanometer, and third case RMS value is 55 nanometer. So, let us make a conclusion here. When you will use the printed circuit board, let us try to use one cleaning method. After the cleaning method, you have to collect your cyclic voltammetry on that surface, okay, and that cyclic voltammetry guide you if the surface is probably clean or not, means delta E value, this delta E value, and you can check like their AFM images and collect their RMS value. If your RMS value is near like 18 nanometer or less than or nearby 10 nanometer, in that case you may think yes, your surface is really clean. But if your root mean square is very high, like see, if you go more and more RMS value, if you see they compare. So, in this case the 18, 41 and 55, see here 18, here 41, here 55 nanometer. It means if the RMS value increase, your surface actually irreversible surface. This is not good for the biosensor development, it is not so clean. So, here you may get some bad cyclic voltammetry for the K3FeCN6, this mixture. So, this roughness value will guide you. Accordingly, batch to batch variability of the PCB board that you can check. Means when in the batch to batch means in the industry, when they are fabricating printed circuit board, few batches may not good for like maybe there may be some fabrication issue, there may be some contamination issue that can affect on your biosensor development. So, for that you can just check cyclic voltammetry, check their AFM images, and you just decide that you can use this one for biosensor development or not. This is very good information. Just try to remember. Then after the AFM study, if you wanted to check that yes, your surface is really clean or not, let us check the XPS, photoelectron spectroscopy, X-ray photoelectron spectroscopy that I showed all the last class. Today again I am summarizing here. You can see that the BC means just before cleaning, AC means after cleaning. See the gold peak, see this is the before cleaning is very less, but after cleaning is very high. It means you are getting the gold peak, it's very high because the organic contaminant almost removed, and carbon contaminant. See the carbon contaminant in the case of after cleaning almost no, but before cleaning there is very high carbon contaminant there. And also we got some copper, because as I told you last class also, while PCB industry they are fabricating gold, on the PCB surface there is a copper layer below, and upper they are using a gold layer. So, during the cleaning process, some copper layer can be exposed, or during the fabrications of the gold also, it may not fabricated very good way. So, you have to check there is some exposed copper layer or not, that you have to verify. So, if your cleaning is very strong, if it damage the gold layer, then you may get some copper peak. That is, if it is very highly intense copper peak, then you have to be very much serious, you have to be very careful, that copper can affect on your biosensor. This kind of information you should have. And then this sensor can be useful for glucose detection. So, today I will show you the glucose detections now. Means this PCB that you got all the information after the cleaning, let us use them for glucose quantifications. So, I already taught you how to modify the glucose oxidase on the PCB surface. Here just we use EDC NHS, then we activated it. Means EDC NHS activations method we use because surface already have your carboxylic group, and that can be activated by EDC NHS, and then we added glucose oxidase, and then glucose oxidase already immobilized on the surface, and then you tried glucose oxidation. Glucose oxidation, and this is a enzyme based glucose oxidation because already you have enzyme on the surface. And this is the actual structures that actually I wanted to show you, the structures of the PCB that we integrated some microfluidics. So, at the very first slides I showed you that microfluidics can be integrated some different way. In this case I am showing you that microfluidics can be just another layer. So, here is two different type of the microfluidics we use, 1 and 2 pattern we use. So, this is like just a simple channel, and there is a different channel, looks like different, that you can try different microfluidics and their efficiency. So, this is the whole setup. So, one way you can inject your solution like glucose solutions through the one inlet, and through the outlet all the excess solutions will be removed. So, and then you can try the glucose oxidations, means once glucose solutions come on the glucose oxidase surface, and then when you apply, you have to apply some potential, right, you can remember, for example just 0.3 volt, then this glucose will be oxidized, you will get the amount of current based on the concentrations of the glucose, and then you can make the calibration curve. And here this is the very important figures, that while you are measuring the glucose, then you have to try to find out the other interference species that may present in the real sample. What kind of interference species may present? Like fructose with the glucose, right, uric acid, ascorbic acid. Then you would try to find out their contributions on your background current. If their contribution on background is very high, then it means your sensor surface is not so good for selective detections of the glucose, because I wanted to see the how much glucose present, not the other. So, because some people they may have some different concentration of uric acid, right, they may have uric acid. So, if uric acid also can oxidize in the presence of glucose, so it can cause the background, it will give some false positive signal. You may think this signal you are getting because of glucose, actually not, because uric acid also can be oxidized. But one important thing, while you are using glucose oxidase is an enzyme and they are very selective. So, it is little bit safe side for you while you are using enzyme, but this can interference species affect, you have to be very much careful when you are using some non-enzymatic procedures, that I will teach you next class. But just this is just for your understanding, while you develop a biosensor, definitely you should check all the interference species present in your real sample and check their contribution. Now, let us come, let us show you how we can implement a patch, right. So, I wanted to develop a very simple patch like Band-Aid, right, and here this patch will use a PCB, but this PCB will be flexible PCB, flexible. Why I am saying flexible? That this PCB substrate should be a flexible substrate. On that flexible substrate, you have to print these all the this all the working reference counter electrode you can print. That can be done easily. Okay. So, if you want to develop a wearable biosensor based on PCB, let's use a flexible substrate like polyimide sheet, something flexible polyimide sheet. You can try. See, something like this. Then this is your microfluidics layer. You just put on this top, and you can use some glue, and you can fix. Your upper part is the microfluidic, and down lower part you have your PCB. Okay. So, this PCB and this microfluidics let put together with some adhesive, and your system should be looks like this. And then you have the your adapter. This adapter you can try just integrate with the potentiostat and just for lab purpose. But when you are thinking for patch development, that time I will show you one patch when something like this, like band-aid, you know. Here you can use like on working electrode, on counter electrode, on reference electrode, like this, and maybe here connection will be like this, and here should be some microfluidic channel should go through this electrode. That I am going to show you in the next slide. But here this slide is a complete information you have. Like, see, in the lab setting generally we are doing this is just a pump. By using this pump we can control the flow of some artificials like interstitial fluid, artificial sweat sample you can use, and then you just flow through this inlet and outlet tube, this tube, inlet and outlet. Because while you use the flexible patch, when you will keep it on skin, then it will take the interstitial fluid, or what is interstitial fluid, you know, that I am going to show you again. So, interstitial fluid it will collect, or sweat sample it will collect, then it will go through the your sensor surface, then it will measure. This setup is the laboratory setup, but now I wanted to show you the actually patch setup. So, here is the data. That data actually you already know, like glucose oxidase, based on the glucose oxidase immobilizations, you can see the different concentration, the glucose current is increasing, then you can develop your own calibration curve. That concept you know already. So, for this development of this patch based biosensor, so you have to collect the interstitial fluid. As I told you, so you need some microfluidic this. So, on this microfluidic there is some inlet, right. So, here your all the interstitial fluid means you can inject and it will go through, but when it is the real patch, then it will collect, it will put on your skin, it will collect the interstitial fluid, but you need some very small needle. So, you may think that this is it then I mean you can say invasive or non-invasive, but when you use the small very micro label, very small needle, that needle can help you to collect the interstitial fluid under the skin, and you will not feel much pain. It is, you can say, invasive but minimally invasive, not that much invasive. We are saying this on non-invasive also you can say, or minimally invasive while you are using this micro needle. This is the micro needle. So, it looks like this, but actual needle is really painful, means while you are collecting the blood samples, but when you use the micro needle it is not that much big, it will not affect, it will not damage your nerve system, so you will not feel much pain. So, it will be looks like this. Then you can integrate this, because when it will come to your skin, then it will collect the interstitial fluid, then that interstitial fluid will go through the microfluidic channel, then it will come to the sensor surface. We can develop a new technology, that is hydrogel based microfluidics. This hydrogel microfluidics is really important for patch development for this kind of painless or minimally invasive patch biosensors, that easily you can attach on your flexible PCB. You can collect the interstitial fluid and you can get the different concentrations of glucose in the interstitial fluid. So, this is the images of the microneedles, and that microneedles, suppose this is the microneedles, right. That microneedle, see, it can absorb the interstitial fluid and then go through the, see, your channel, it will come to the your sensing part, your sensor part, and then your sensor is ready for detections. And this information that I wanted to share you already know interstitial fluid. This is just a body fluid just under the skin, and there is a difference between the interstitial fluid and plasma that I already mentioned here. So, plasma means just you may get colorless from the blood, but interstitial fluid just below the skin. So, just see this difference between the interstitial fluid and the plasma, that is just for your more, you may get more information. But using the micro needle, this interstitial fluid can go through the like this channel, and you can detect the glucose. This is just one patch development. I will show you again this all the whole systems with the electronic part again next class. But just I wanted to tell you in this class that surface cleaning of PCB is really important for biosensor development. I just started with the PCB for biosensor for glucose detections, then I will show you more example for biosensor development using the PCB. But today's class you just learn that PCB can be useful for detections many and light, but you have to be careful their surface cleaning method and surface roughness, their main cyclic voltammetry you have to measure before the electrochemical measurement. Okay, thank you. That's all for today's class.